Welcome to an introduction to set theory. In this video, we will discuss vocabulary, containment, also known as subsets, and power sets, operations on sets. In a follow-on video, we will continue with operations on sets, go on to laws of set theory, counting and Venn diagrams, inclusion and exclusion, and we'll have a quick word on probability. Probably the most well-known application of set theory are relational databases. So if you've ever looked at SQL, you'll see a lot of symbols as well as a lot of ideas that come from set theory. We will start with vocabulary. A set is a well-defined collection of objects. The objects are called elements and are said to be members of the set. Little correction there, members of a set. By well-defined, we mean for any element we choose to consider, we can determine whether or not it is in the set. For example, the set of outstanding movies is not well-defined because while I would include 2001, many other people, including members of my own family, would not. We use capital letters, such as A, B, and C, to represent sets, and lowercase letters to represent elements. We write X is an element of A if X is an element of A. We write Y is not an element of A, so here you have the crossed out symbol, if Y is not an element of A. More vocabulary. A set can be designated by 1, listing its elements, for example, A equals 1, 2, 3, and 4. Or 2, you can designate a set by qualifying by stating properties of its elements. For example, A is equal to all elements that are between 1 and 4, such that X is an integer. The cardinality of a set denotes the number of elements. The cardinality of a set denotes the number of elements. So for example, A is the set with the elements 1, 2, 3, and 4. It is equivalent to the set 1, 1, 1, 2, 3, 4, and is also equivalent to the set 4, 3, 2, 1. So order doesn't matter in sets, and neither do repeated elements. In all cases, the cardinality of A, designated with this or denoted with the absolute value, is equal to 4. There are 4 elements. The next example, set B. Now B is a set whose elements are sets. In other words, it is a set of sets. And in fact, B is the set containing the set A. The cardinality of B is equal to 1. So I've written this down one more time. B is a set of sets. That is, its elements are sets themselves. The null set, or empty set, is the unique set containing no elements. It's denoted by this null or by the empty set. The universe of discourse, this is my script bold U, which actually looks better in the textbook than on here, but it's the set of elements we consider as possible elements. There is the universe of discourse. Sometimes we discuss Z, the set of integers, Z positive, the positive integers, the natural numbers, which includes the 0, and R, the set of real numbers. So we've discussed vocabulary, and now we can talk about subsets. Before we start talking about set containment, I do want to say a word about Venn diagrams. More than likely you have seen these. These are these boxes that kind of represent our universe of discourse, whatever universe we're discussing, and then we draw sets, we draw circles to represent sets. So everything in this circle is in set A, and then you might have little points to represent elements in set A. Over here, you might draw everything in set B, and you notice there's some overlap. So these are elements that are in both A and B. And then you might have said everything, if you look over here, everything in A and everything in B, you might have said something like that's equal to A union B, which we will discuss later. And then you might have seen, of course, the intersection again, the elements that are both in A and B. So Venn diagrams are a useful tool for visualization, and you will see that I do use them to give me insights when I'm working different problems. But you will also notice they are not sufficient for proofs. Among other things, to start with, to use a Venn diagram as a proof, you would have to somehow prove that your Venn diagram represents all possible cases. But as I said, you will notice I use them to get insights, but then you'll also notice I will do formal proofs. Now we are ready to start containment, or subsets. We say C is a subset of D, and we write C is contained or equal in D, so the contained sign sort of looks like a C, standing for contained. If there exists, if for all x is an element of C, implies x is an element of D. We say C is a proper subset if 1, C is contained in D, and there exists a y such that y is in D and y is not in C. The notation for proper subset is this C is contained in D. So in this case, the difference between being just a subset and a proper subset is if you're a subset, possibly C is equal to D. If you're a proper subset, then you are not equal to D because there's something in D that is not in C. And then last, we say C is equal to D, and we write C is equal to D if 1, C is contained in D, and 2, D is contained in C. Now, in this definition here is really the first time in class that you'll see this huge difference between engineers and mathematicians. When you give a definition to an engineer, the engineer will really work with whatever you give him, and that's how the engineer will understand, is basically they'll work with it. For a mathematician, the definition really is everything, and mathematicians take definitions as pretty much the last word of everything. I don't know if you've ever noticed when you read a math book, they're very exact. Every word is important. They won't tell you there is one solution. They will tell you there is exactly one solution, or at most one solution, or at least one solution, and that one word in front makes all the difference. So, why am I harping on this? It's because later, when you want to show something is a subset, if you want to show C is a subset of D, you're going to have to go back to the definition, and you are going to show that for all x, if x is in C, then x is in D. And unless you can show that, you have not satisfied the definition of subset. But we'll do some proofs later, and for now, let's just get a feel for the definitions. We will start with some sets. We have the set A, which has the elements 1, 2, and 3. We have the set B, which has the elements 2 and 3. We have the set C, which is a set of set. It contains one set, which has the elements 2 and 3. And then we have the set D, which is also a set of sets. It contains the set 1, 2, 3, as well as the set 2, 3. So in other words, D is the set containing the set. This should be A and B. Okay, so now here we have D is the set containing the sets A and B. The first fact is we have B is contained in A. So what does that mean? If B is a subset, or a proper subset of A, in this case, then 1, we know it is a subset, which means that every element of B must be in A. So we have two elements of B, 2 and 3, and both of these elements are in A. It's a proper subset because there is something in A that is not in B, that is 1. We also have that C is a subset of D because everything in C, and there's one element in C, the set 2, 3, is also in D. It's a proper subset because there's an element in D, the set 1, 2, 3, which is not in C. We have A is an element of D because here is A, which is an element of D, but A is not contained in D because A contains the element 1. D does not contain single elements, it only contains sets. So in particular, A has the elements 1, 2, and 3, and none of those are in D. And last, we have B is not equal to C because B has the elements 2 and 3, neither of which is in C, and C has the set 2, 3, and which is not in B. B contains these single integers, C contains sets. A second example, if A is the set X such that X is divisible by 5, that should be an X, and B is the set X such that X is divisible by 10, prove that B is a subset of A. So just to remind myself, to show that B is a subset of A, I'm going to go look at the definition of subset, and I'm going to rewrite it in terms of A and B. So we need to show for all X is an element of B implies that X is an element of A. And again, I'm going to reiterate, this is, in order to show this subset, we have to use this definition. This is what we need to show. And nearly all proofs of containment start with this statement right here. Let X be an element of B. Because here we're saying what we want to show is if X is an element of B, it's an element of A. So this is pretty much nearly always the first statement in a proof of containment. Well, if X is an element of B, then X is divisible by 10. My justification for this statement comes from the definition of B. My next statement, well, if X is divisible by 10, then X is divisible by 2 and 5, and that just comes from arithmetic and the definition of divisible or factors. So then I just rewrote X is divisible by 5 just for emphasis, and if X is divisible by 5, then X is an element of A. Again, by definition of A, and therefore X is in B implies X is an element of A, which means B is a subset of A, and I am done. Now from our last example, we can find some important points for containment proofs. The first point is all correct proofs use the definition of containment. In this example here that we had, we specifically wrote out the definition of B is contained in A means that for all X, X is in B implies X is in A. Second important point, nearly all containment proofs start with the words let X be an element of name of subset. And you can see that right here. Let X be an element of B. And in this case, B is what we're trying to prove is the subset of A. The pattern then is once we have our element of the subset, we use properties of the subset and any other relevant information given or that we have to show that the element also has properties of the containing set. So in our example, we said once we had an element of B, We looked at the properties of an element of B, and then we showed that those properties also are enough to make it an element of A. The last point, proofs end with generally near the end. X is a member of name of containing set. Here that is in our example. Of course, if you have to prove that something is a strict subset or a proper subset, you'll also have to do the second part of the definition. Or if you have equality, you'll have to do the second part of the definition. But this is the general format or pattern that you're going to use for containment proofs. It's really important you use this format because when you see this on an exam, and I hate to bring it up this way, but you're almost certain to see at least one of these on one of your exams, and when you see it, I'm really looking for this format. I'm not looking for a huge long essay or story. This is what I want. So for containment, there are some transitive properties. The first is if A is a subset of B and B is a subset of C, then A is a subset of C. The second, if A is a proper subset of B and B is a subset of C, then A is a proper subset of C. And then we have C and D. So as another example of these proofs of containment, and also that format that I really am looking for, I'm going to do a proof of part B. If A is a proper subset of B and B is a subset of C, then A is a proper subset of C. And again, if you look, the first important thing to do is to make sure you're using the definition. So I kind of remind myself, if I want to prove that A is a subset, a proper subset of C, we need to show two things. We need to show the first part of the definition is satisfied, that is, for all x in A implies x in C, and two, we need to show that there exists a y that is in C that is not in A. Now, again, the first step, we're going to write let x be a member of the subset. So we're trying to prove that A is a subset of C. Therefore, I have let x be a member of A. And so what do we know about A? Well, we know A is a subset of B. So if x is an element of A, then x is an element of B. And that is because we are given A is a proper subset of B. So what else do I know? Well, I'm also given that B is a subset of C. So if x is in B, that also means x is in C because we are given B is a subset of C. But now we have shown what we need to in order to show that A is a subset of C. Therefore, A is a subset of C. Now notice we haven't shown it's a proper subset yet, so we have one more part to do, and that is the second part here. We need to show that there exists a y that is in C, but not in A. So I'm looking to see what we know. So we know that A is a proper subset of B, which must mean there's something in B that is not in A. So I've written this down. So there exists a y such that y is in B and y is not in A. And we know that because A is a proper subset of B. But this y is in B implies this y is also in C because we are given B is a subset of C. Therefore, there exists a y such that y is in C and y is not in A. And so we are done with our proof. We've shown both steps. We've shown that there's something in C that's not in A, as well as showing that everything in A is also in C. So we've just finished containment and subsets, so now we can talk about power sets. We'll start with the example. The power set of A, denoted P of A, that should be kind of an italicized P, but P of A is a set of all subsets of A, and you want to note that the null set is a proper subset of any set. So an example, let A equal the set 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. How many subsets of A contain 6 elements? And I'll give you a hint. This comes from Chapter 1, Combinatorics, which you will see again in Chapter 5. There's no getting away from it. But anyway, how many subsets contain 6 elements? So this you should be able to answer. So maybe you want to pause, give it some thought, take a guess, and then restart. But I'll tell you the answer here. It is 12, choose 6. Because remember, for sets, order is not important. So from the 12, you just want to choose 6. Our second example, how many strictly increasing sequences start with 1 and end with 7? Again, you might want to pause and take a guess because you should already know enough to do this example. Actually, that's probably true of all examples. But let's just, so go ahead and pause. But here's the solution. So examples of strictly increasing sequences that start with 1 and end in 7 are 1 and 7. That's the smallest one. We could have 1, 2, and 7. We can have 1, 2, 3, and 7. Or we could have 1, 3, and 7, etc. But the important thing is we always have the 1, we always have the 7, and besides that, we are choosing numbers from the set 2, 3, 4, 5, and 6. Now in this case, the order is important, it's strictly increasing, but actually it's not that important because once you choose the number, then there's only one way of putting them in increasing order. So essentially what you're doing is deciding whether or not you want to include the 2, and then you're deciding whether or not you want to include the 3, and then the 4, 5, and 6. So it's a multi-stage process. At each process you're deciding whether or not to include the 2, 3, 4, 5, and 6. So, and then because at each stage you have 2 choices, to include or not to include, your answer is going to be 2 to the 5th, or 32. That's how many strictly increasing sequences there are. Our next question, if the cardinality of A is equal to n, which is greater than or equal to 0, what is the cardinality of the power set of A? So take a minute to think about it, and just if you need a hint, it's kind of related to number 2. So as I said, it's kind of related to number 2 because for each of the n elements of A, we are going to decide whether or not to include it in this set. And so there are going to be 2 to the n ways of deciding whether or not to include things in sets, and therefore that's going to be the number of power sets. And when I write it, I'm just going to write it kind of with that cursive. So I wrote this down just in case it's easier for you to see once it's written. So the solution is that this is an n-stage process where the nth stage decides whether or not to include the nth element. And whether or not to include, that means there's 2 choices. You can include or not include, and that's where you get the 2 choices for each of the n stages. You're multiplying 2 n times, so you get 2 to the n. So there are 2 to the n possible ways of including or not including, and that will give you the 2 to the n subsets. The last example is more of a discussion than a problem. So I wrote down this combinatoric identity where 2 to the n is equal to n choose 0 plus n choose 1 plus n choose 2 all the way down to n choose n. So what we can get from the power set discussions is kind of a feel why this is true. So first, 2 to the n, that's the number of power sets you have. This will also give you a little more insight into how 2 to the n becomes equal to the cardinality of the power sets. So the number of power sets you have is equal to the number of subsets with 0 elements, and of course that's the null set, plus the number of subsets with 1 element. And you go on, and choose 1 is the number of subsets with 1 element. And here there's also the next term is n choose 2. That's the number of subsets with 2 elements, up to n choose n, which is the number of subsets with n elements. So these are all possible subsets, which is equal to P of A. Again, what you get is kind of this proof of this combinatoric identity. So we've done vocabulary, we've done containment and subsets, we just finished power sets, so now we can start operations on sets. So operations of sets, these are basically the arithmetic of sets. So we'll start with the first, which is the union. So we write A union B are the elements X such that X is in A and X is in B. And a Venn diagram is helpful to see this. Here's everything in set A. Everything in this circle is what's in set B. So everything in A and everything in B, that will be our union, A union B. Next is the intersection, and we write A intersect B. And A intersect B are all the elements X such that X is in A and X is in B. And in our Venn diagram, that would be everything here, both in A and B. Next is our symmetric difference, A symmetric difference of B, written with this little triangle. I actually don't use this a lot, but sometimes it comes up in the book. So A is in A union B, and X is not in A intersect B. So the symmetric difference is going to look like everything in the union, but you take out the nothing in this intersection here. Then we have complement. So A complement, denoted with the bar on top, is everything in the universe that is not in A. So A complement, if this is the set A, everything out here is A complement. So relative complement, that's B minus A, is everything in B that is not in A. So that's the relative complement, B minus A. One last definition. Sets S and T are disjoint when their intersection is the empty set. So an example of some of these set operations will let A equal the closed interval 0 through 3, and B the half-closed, half-open interval 2 through 7. And just to remind you what these intervals are, so A is the closed interval 0 through 3, so that means it includes the endpoint 0, and it goes up to the endpoint 3, because we're dealing with real numbers. B, I'll draw in blue, it includes the endpoint 2, and it goes up to, but it's open, so it does not include 7. So all the way up to 7, but not including 7. So the first thing we can look at is, oops, let me do this in black, A intersect B. So over here, A intersects B between 2 and 3. And if you look, both A and B include both endpoints. So I have the bracket. Our next example, we can look at A union B. So in this case, A union B goes from 0, including the endpoint, up to 7, but not including the endpoint. So it goes from 0 to 7, not including an endpoint. Last, we can look at A symmetric difference, B. And just to remind you, I wrote the definition of symmetric difference. X is in the union but not in the intersection. So if I look over here, here's the union, here's the intersection. So it includes everything in the union, so it's going to include 0, and everything up to, but not including the endpoint, and then it's going to omit the intersection. So we have 0, and then we go up to 2, but we don't include 2, and then we're going to union that with 3 to 7. So to conclude this video, I just wanted to mention a proof example that we will complete in the next video. But this example is an example of a proof. It has concepts from containment and how to prove something's contained or a subset of something else. It has set operations. It actually has a proof by contradiction. It has all kinds of things. So I thought it would be a good example, and I wanted to mention it here, but we will complete the proof in class and in the next video. So the proof we are going to do is of this theorem. Sets S and T are mutually disjoint if and only if, that's the bidirectional implication, if and only if S union T equals S symmetric difference T. So now we have completed vocabulary, containment and subsets including power sets, and we are nearly done with operations on sets. We will pick up in our next video with that proof that illustrates many things from the containment to operations, as well as just a good example of a proof. We'll also do laws of set theory, counting and Venn diagrams. That leads us to inclusion and exclusion, and a quick word on probability. Thank you for listening, and I'll see you in class.